We have some understanding of how electrons behave in bulk materials. We're ready to turn to examine the first of our nanoscale phenomena. By far the most important, I think, is what happens in a very small contact. So I'm showing here two reservoirs of electrons, two metals, connected together by a tiny channel. What do I mean by tiny? Well, I mean on the order of the Fermi wavelength. Recall that the Fermi wavelength is about an angstrom. So if this channel were to be 1 angstrom in diameter, only one quantum state could fit inside this wire. It turns out that in those conditions, the resistance, or more commonly 1 over the resistance we like to talk about, the conductance of this channel, is a universal number. Let me tell you that result because it's so useful. The result turns out to be that the conductance of this channel is just 2 the electronic charge squared over Planck's constant. Conversely, the resistance, called the Landau resistance associated with this channel, is just h over 2 e squared. This is about 12.9 kiloohms, and this is about 77.5 microsiemens. Now, this result immediately solves the problem of how much current am I going to get through my scanning tunneling microscope, because we know that when the STM probe touches the surface, since the STM probe has most of the current emanating from the atom at the end, that this is a problem of a quantum point contact, that the resistance in contact must be 12.9 kiloohms, and therefore the resistance of the junction must increase as e to the 1.02 square root of phi times the width of the junction. The conductance, of course, would be 77 microsiemens times e to the minus 1.02 root phi times the distance of the junction. So now we can give an absolute calibration to tunnel junctions. How is this quantity derived? We derive it using Fermi's golden rule, and this says that the probability of a transition from the left electrode to the right, where here I'm showing an energy diagram. So what we've done here is to apply a negative bias to this electrode, so we've raised the Fermi energy of this electrode relative to the second electrode by the electronic charge times the voltage V applied between electrode 1 and electrode 2. If the two are in contact, the transmission probability is unity, and so we are left then just with counting the number of states available for electrons to make a transition from here to here. Let's make this quantitative. The current is just given by the product of the charge per carrier times the number of carriers crossing the barrier times their velocity, which will be the group velocity for electrons in the particular quantum state allowed in the channel. Now, the number of electrons crossing that barrier, let's just redraw that little diagram here. We had one Fermi energy up here and another down here, and so we're tunneling into these empty states. The energy width of is E times V. So N is going to be the number of states per unit energy times this energy EV, where V is the voltage applied to the gap. We can play a trick here and write dN dE as dN dk times dk dE times EV. But remember that the group velocity is given by 1 over h bar dE dk. So dk by dE is just equal to 1 over h bar vg. So if we go back to our expression for the current, I, well, it's going to be the number of electrons per k state, which is 2 for spin up and spin down, so we'll put the 2 in here. And then maybe we have more than one quantum channel, so I'm going to put the n in here. And then we have the electronic we have the number of states, and that is then just 1 over 2 pi. Why? Because that is dn dk in one dimension. This was a result we derived in chapter 2. 1 over pi, 2 pi, dk dE then was 1 over h bar Vg, times this energy range, the electronic charge times the bias applied, times E, and times Vg. Look at what happens here. Vg is the one material-dependent parameter here. It's the group velocity, which depends on the curvature of the bands in the state allowed into the channel. This disappears from the expression for current. So in the case where we have one quantum channel, like our STM tip, the current then is just given by 2 E squared, 2 pi h bar is just h, times V. So if we use V equals IR, or alternatively G equals I over V, we can derive the values for the Landauer conductance as 2 E squared over h, or the Landauer resistance as h over 2 E squared. So this is a remarkable result. It says that a quantum channel will have a universal resistance or conductance. So we can see this behavior in real life. One way to do this is to simply make an experiment in which we pull apart a gold wire. So we may cut a nick in a gold wire like this, and then just pull it apart. We can do this actually by advancing a gold STM probe onto a gold junction, and in gold the effect is particularly drastic. As we pull this to pieces, while measuring the current through it at some bias V, what we observe, and real data is shown in this slide, is that the current drops in precisely equal quantum steps. And knowing the voltage, if we work out the conductance associated with each step, we see that it is indeed 77 microsiemens. So this is a demonstration that you can do with a piece of gold wire, a piezoelectric element to pull it to pieces, and then an oscilloscope to record the current. This might be current against time. One final use for this very remarkable result is to calculate the conductance if we are not actually in contact. This will turn out to be very useful in molecular electronics. So a result due to Landauer and Buttiker is that it is this universal conductance, 2E squared over h, but times the sum of all the transmission probabilities through the various channels connecting one electrode with the other. And it turns out then that by using quantum chemistry programs, we can calculate this mysterious Tij squared quantity, and thus the absolute conductance of a junction containing even a complicated molecule.